Alright, hello and welcome back to another video where today we will be plotting the different isotherms of the cubic equation of state, specifically that for SRK. Okay, and let's go through what I have up on my screen right now. Just some starting materials, right? I just copied down what was in the textbook, going through all the different expressions within the cubic equation of state, and then some other useful stuff that we'll be going over later. And on the right hand side we have our standard imports. We have Carlos's CHE tools package. Okay, and let's make sure those are running really quick. And we're using sys to put that package in the very first thing that Python looks for when we import. Then that allows us to actually import the package. Next, we're importing numpy, and then we're going to import scipy.optimized root. We'll use that later. And then we're using all the plotly stuff in order to actually plot our isotherms. Then defining the universal gas constant R, and then just defining an object P to be our properties of water. Okay, let's get started. If we look over here, this is what we actually eventually want to plot. But you'll see that there are some unknown values, right? There's B, we don't know what B is yet, epsilon, sigma, and this function A of t, the function A dependent on temperature. And that's all given down here. So why don't we create a Python function called ABES, a Python or cubic underscore ABES. In other words, a Python function that is going to give us our A, B, E, and S parameters. So it's going to return A, B, E, and S. And we'll work backwards from here, okay? And I'll throw in T as an argument because, well, we know for a fact that T is going to be, it's going to determine what A is going to be. So we know that T is an input, essentially. And we'll start with some of the easy things first, okay? We'll look down here, sigma and E are just, for SRK, it's just 1 and 0. So S equals 1, E equals 0. Oh, great, we have half of our function done already, right? Next, let's look at the second easiest thing to define. B. B is equal to capital Omega RTC over PC. Okay. B is equal to Omega times R over T P dot TC times or am I doing that wrong? Oh, I did do that wrong. R times T P dot TC. And let's throw in some parentheses, because I'll tell you what, this is not the first time I recorded this, and a lot of these errors come from not paying attention to details and dropping parentheses. So let's make sure we do this right. Over P dot PC. Okay. Okay, great. We have B, E, and S, but we don't have A. Oh, that's right. Before we do that, omega is not defined, right? What's omega? What's omega? Well, if you scroll down here, omega for SRK is just a value. Omega is equal to, what's that value? 0.08664 for the SRK cubic equation of state. Okay, let's tackle A. What's A equal to? A is equal to psi times, let's open some parentheses, A, well, this is actually a function, alpha, that's dependent on the reduced temperature and the eccentric factor. We'll go over that in just a second. Why don't we just build our equation for the time being? Alpha, this is in the numerator, alpha times R squared. Okay. Let's throw in some parentheses. Okay. R squared times P dot TC squared. Throw that in parentheses too. Match up our parentheses. We're A-okay. Okay. Everything in here is our numerator. Divided by P dot PC. Okay. Let's take a look at this. we have alpha. That's our only, oh, alpha and psi are our two undefined variables. What's psi? Let's do the easy thing first. I always do the easy thing first, right? Well, psi for SRK is very simply a number. Psi is equal to 0.42748. Okay, easy as pie. Alpha is a little bit more involved, but still conceptually simple. Alpha for SRK is equal to this ugly expression. So, in order to keep ourselves in check, we'll work out from the outside in. We know for a fact that the entire quantity is being squared, so why don't we do that first? Then it's 1 plus 0.480 plus 1.574 times the eccentric factor. What's the eccentric factor? Well, I personally don't know yet. But I know it's a factor that, oh, that's right. I do know. Sorry. I believe the eccentric factor describes the non-sphericity of a gas particle or gas molecule, and it's a property that's dependent on the type of gas you have, the compound that you have. Okay, but in this context, it's a number that allows us to plot our cubic equation of state. Okay, a little bit sidetracked, but next term 0.176 times the eccentric factor raised to the 1/2 power. 1/2. Okay. Great. Okay. That whole quantity times 1 minus TR raised to the 1/2. Oh, my apologies. This is raised to the 1/2 power. 1/2. This is not raised to the 1/2 power, it is squared. Squared, right? And it appears we have the correct number of parentheses. Now, you might be wondering, well, what's TR? TR is very simply just the reduced temperature, or in other words, T over T, the temperature divided by the critical temperature. That's all it is. Okay? And with that out of the way, I believe that our cubic ABES function is complete, which allows us to go back and build a function that allows us to compute pressure. So cubic P, the cubic equation of state for pressure that is dependent upon temperature and volume, is, we'll return. We'll just do a one-liner, okay? Return the entire expression. But we need to get our ABES. So the way we do that is A, B, E, and S is equal to cubic underscore ABES T. Easy peasy, right? Next, we are going to, very simply, well, plug in our equation. R times T over V minus B minus A over V plus E times B times V plus sigma times B. My apologies, that should be a V. Okay, make sure our parentheses match up. Fantastic. Does that, alright? Well, let's debug and double check, okay? Cubic underscore P. If I can type, holy moly. We'll do 400 and 100. Okay, returns that. Let's check that against a known working function. It's very much incorrect, but I've seen this error before, and I believe that it comes down to a parentheses mismatch. And it's usually within the alpha function. Check that out. There it is. Or is that true? 1 plus this quantity times this quantity. We'll do a quick cut, do some debugging, and I'll find out the root. Root out the bug. Okay, well, we're back, and well, things should be working good now, because all I really did was rewrite the return function, and I believe there is a parentheses issue causing problems. But without further ado, let's go ahead and get started with the graphing. So first thing we want to do is create our figure. Figure equals make underscore sub plots, right? And we want to have a set of data to plot, and our data is volume. So we're going to do the standard length space, and I'm telling you right now that this is wrong, okay? But we'll do it wrong first, so that I can explain to you why we do the things we do to make it right, okay? And a little bit about non-ideal gases. Remember that a non-ideal gas is essentially saying, okay, remember those things that we generally ignore? Well, we're no longer to ignore them, and we're going to assign correction factors, and those things being the actual volume gas molecules take up, and the van der Waals forces between each and every gas molecule. They're no longer non-negligible, and we want to account for them through a correction factor. Well, the correction factor that we're interested in is B. B is the correction factor for the actual volume that a gas molecule takes up. Sorry, not a gas molecule, the actual volume that all of the gas molecules in a system takes up. Okay, so the way that we do that is, in other words, it's equal to our minimum volume, right? And our minimum volume is equal to the expression for B. There we go, minimum volume. And now we can start thinking in terms of percentages. So we can say that, okay, we want to start at, I don't know, 1% above the minimum volume, and we'll go all the way to something like 182, the minimum volume, and we'll have something like 500 points in between. Okay, well, let's make our P. P is equal to cubic underscore P volume and temperature. And we'll say temperature is equal to something like 400. Okay, let's plot it. Well, fig.add scatter v fig.add scatter x equals v, y equals capital P, cubic P. Couple of syntax errors. So look at that. Let's talk about this graph. Well, we have a lot of boring stuff here, but look at this. Something interesting is happening at a very, very small value. Okay? Well, that doesn't make all of this stuff not important, right? But we want to visually represent everything that, I don't know, that a human can look at and draw conclusions from. So, the way that engineers and scientists do that is with a logarithmic plot. And luckily for us, Plotly has a built-in function, update x-axis, for logarithmic plot. Type equals log. Well, look at that. We can see some behavior now, but this reveals another issue. Look at those straight lines. Well, what does that tell me? That tells me that, well, you know what did I show you? Oh, what did I show you? Mode, we'll change the mode to marker so we can debug and say, we can see where our data points lie. Okay, look at that. Lot nice of tight data points that can form a nice smooth line, goes a little bit negative, and then, totally missing data. Totally missing data. Okay? And the reason why that happens is, well, we're dealing with a logarithmic plot, but our space, our data is linearly spaced. Well, guess what? NumPy has the solution for you, log space. Okay? And in log space, each argument is actually the power of 10. So the way we deal with that is numpy.log 10 of this. We still want to think in percentages, and we'll actually change this to, well, we know that over here it's like something like 0.001, so we'll make the maximum like 10 to the negative 2. Excuse my voice crack. Okay, look at that. Look at that. We see the beginnings of that, you know, van der Waals loop, and then the behavior of a 1 to the x. So that's an isotherm. What if we want more than one isotherm? Well, luckily for you, Python has got your back with the Python for loop, 4t in range, something like, I don't know, 275 to 800, increment by 25. We're gonna, in that range, we're gonna recalculate p, right? And then we're going to render a new curve for every time we recalculate b. Let's go ahead and do that. Colon, don't forget your Python syntax, guys. Alright, look at that. Oh, beautiful. But not so much. We have a lot of interesting action happening here, like a very, very small part of our screen. We want to blow that up, right? But we still want to keep our logarithmic scale. I think our logarithmic scale is good because we want to say that, okay, all of these converge to 0, right? But we still want to see, okay, what's happening in this neighborhood, right? And, you know, Plotly lets us do this, right? We can clearly see that van der Waals loop, but we want this to happen every time we render. So the way we do that is we use a range, fig.update. Remember range from, I don't know, high school, guys? So, range. And I think the way that Plotly likes the range is in an array. We'll do, well, this goes all the way to the billion, so we'll do like a minimum of negative 200e6 to 200e6. Something like that. And there you go. Look at that. We have a whole bunch of isotherms, so we can clearly see our van der Waals loop. And that is, to be honest, a very visually pleasing graph. Imagine trying to do this in Excel. It'd be very tedious and, to be honest, quite nearly impossible. Well, that wraps up today's video. Today you've learned how to plot a PV diagram of many, many different isotherms within Excel of, not Excel, within Python of the cubic equation of state, specifically the SRK cubic equation of state. Thank you.